last presentation on this session is about diagnostic methods. We have Paula Lopez-Arce, if I said that right, from Property Care Association. So welcome.
Good morning, everyone. So I'm going to present the results of a project, of a collaboration project between the academia, UCL, University College London, the industry of dampness in construction, which is a trade association, Property Care Association. So this is under this was under a knowledge transfer partnership program. That is, the project is partially funded by the Innovate UK, the Technology Strategy Board, and Property Care Association. So the origin of this project that we thought was very interesting to do research on this topic is on residential atmospheric moisture diagnosis. And this is because condensation and mould is one of the largest damp problems in many countries. Actually, in the UK, more than 500,000 buildings are affected by this problem. So this was a very good opportunity to work together between the academia and the industry, because the mold remediation market is largely untapped, so it's still non-explored. And also there are many things to do research on this topic. So just a little bit of background on this. Mold growth in UK in buildings, it has been identified due to or linked to low temperatures in the buildings, high humidities or very high occupancy densities. And also the reasons for this, or the cause that has been identified, are poor ventilation of the buildings, irregular heatings, or poor thermal quality of the envelopes, and obviously as well a high production of moisture, which this increase the risk of having mold growth, condensation, and eventually a lower indoor quality. So even though mold has not been scientifically proved that it can be toxic, still we know that the high indoor moisture levels in the environment can be harmful for the people that is living due to the microbial growth and other issues like allergies and so on. So this can have controversial implications on the health and the quality of life of the people. And this is a very important topic in the sense that it's very important to identify the causes in order to take correct remedial actions. So the interest for a healthier environment has increased the need of finding more effective methods to avoid inaccurate and inexpensive interventions, or also disrepair claim conflicts. And actually, in the UK, very recently, the renters are able to take landlords to court if they don't fix the damp problems in their properties. So this is why, the problem is it's quite complex to determine which is the root cause of the problem and who is the origin, which is the origin of this. So that's why a robust diagnostic method may support and help the occupants, the tenants, and social or private landlords or homeowners. So even though there are many research studies trying to identify the ways to avoid moisture and mold growth in buildings, still the data measured from buildings is quite scarce. And not also that, nowadays as well, surveyors, or building inspectors, when they go to the building, they don't have standardized procedures, so they are based mostly in snapshots, which can be quite subjective. So this can be costly, and sometimes this takes place when the problems of mold are already there. So there is a need of having accurate, standardized protocols for assessing moisture. But still, as I said, there is a lack of an integrated methodology. So this is the main goal and the objectives of this collaboration research project was to standardize these methods currently used by the surveyors, to develop a robust assessment protocol, and then eventually a commercially viable diagnostic tool for moisture remediation, following the objectives of processing bulk data from environmental monitoring of buildings using environmental sensors, and also developing a methodology using this environmental data and also information from building surveys and questionnaires. So the methodology basically has a first part, which is the selection of the environmental parameters, which are key critical thresholds to be used as a diagnostic indicators to avoid these moisture problems. So there are a whole range of parameters and thresholds, so we had to identify which were the key parameters in order to develop this methodology that relies on linking key surface and environmental parameters on the external walls of the building, like temperature factor or water activity, and then the surrounding conditions, like temperature, vapor pressure, and others. And then to relate these to the impact factors that give rise to produce mold growth when there is an excess of moisture. And basically these impact factors are the poor thermal envelope, if there are no insulation, or there are some thermal bridges, low heating regime, or insufficient ventilation rates. Then the second part of the methodology is the data collection. So the monitoring, environmental monitoring of internal and external conditions of the building, which is very important and critical, since this is the guidance to perform the monitoring right and to know how many sensors we need, the type, the location, and the position of these. And then to support the diagnosis, there is this second part that is a social survey with some questions regarding the building characteristics, the type of ventilation and heating system, and then lifestyle activities related to the occupants and how they produce moisture. So this project took place during 2 consecutive heating seasons, winter 2018 and 19. It involved 30 participants, mostly PCA members, surveyors, but also UCL and PCA staff. So we also provide our own houses. So we were monitoring more than 50 buildings, but we were working with 50. Any kind of buildings like flats, bungalows, and houses from different UK regions, with and without mold problems, because those without problems were used as a reference, so they were very useful for us to have a level of acceptable moisture levels. Then the sensors that we used in each property, we were collecting temperature and relative humidity to monitor the internal and external conditions where the mold was located, or potential rooms, wet rooms. Then we measure as well surface temperature on the mold surfaces, and then we collect as well other environmental temperature and humidity in different rooms to have more information. So we collect this data every 30 minutes during 2 to 4 weeks monitoring period. And the results basically, well, just to highlight as I said, the influence of these positions of the position of the loggers is very important. And just to show you an example is a kitchen with an external wall, an internal wall, and in the external one, if we place the logger where the mold is located, we see that the data falls in the area of risk of mold growth and surface condensation. But if we move this logger a little bit far from this point, the data also falls in a more safe area. And also, if we measure with we locate the loggers in an internal wall where there is no mold, we can see that the data is in a safe area far from having risk of mold growth. So this is very important, especially when there is no mold present, and we need to choose where to locate this. And in this case, it's necessary additional complementary tools like infrared thermal cameras or surface temperature meters in order to find the right spots. Then we were working with the data from the surveys and the monitoring. So we were building databases with this information and also with the characteristics of the lifestyle of the occupants and making relations. And then we realized that we were able to distinguish some distinctive features between dwellings with mold and without mold, like, for example, related to the occupancy, like the home schedule, so those people having more time at home were living in moldy dwellings. And for example, also another distinctive feature is regarding the dwelling is the type of room, the orientation, north-facing, more prone to develop mold compared to other orientations, if the walls are solid or cavity. And then obviously the ventilation is also a key factor, an impact factor. So if the doors in the dwelling are most of the day open or closed, that is going to condition the development of mold or not. So we were also proposed a moisture impact indicator for measuring the impact of the different key environmental parameters. And then to support this root cause of the mold growth related to the thermal quality of the building envelope, the ventilation and the heating, doing relation between these parameters, having some scores when these exceed the thresholds. So far we collect the data from survey forms and environmental sensors from mold, properties with mold and without. We download this data and we were able to know which were acceptable moisture levels, because in the literature we were not able to find these values. We also download this in our calculations, using also the thresholds from the literature, standards and regulations, in order to have a diagnosis on condensation and mold growth and to have a root cause analysis of this. And just to show you now some examples of diagnosis in properties with and without mold and the difference between both. So here is how it looks like the dashboard, where we have a building moisture index with different scores of the impact factor of each environmental parameter, from extremely high to very low or no sign at all, and then some scores. And this is an example of a social house with mold problems. So compared with very high scores in all the environmental parameters, how they influence. And then another example of a property with no problems at all. So we have here, we can see how in the house with mold property, all the data fall in the area of having a risk of mold growth and surface condensation, and how the impact of having a poor thermal quality of the envelope is extremely high, and also the data falls in the wet environment risk area, and this is related to extremely high poor ventilation. So compared to the house with no problem, we see how the data moves from a non-balance or unbalance regarding moisture environment to a safe area, far from having risk of mold growth and condensation, and very low impact factors of dealing with this. And then another example of the usefulness, let's say, of this tool is performing a diagnosis before and after changing a ventilation system. So we see what is a previous version where we see some graphs, and that is what currently the surveyors are using. And we see that, well, we can see some difference, but it's not really quantifiable. So for example, regarding surface temperature and dew point is something that surveyors are using to know if surface condensation is going to take place. But here, with the results, we can see that before the installation of the new ventilation system, how the data is showing us a lack of ventilation and also risk, a very high, extremely high risk of having mold growth in the property. And then once the new ventilation is installed, we can see how the data moves from risk areas of having surface condensation and mold to areas, safe areas, far from this risk of having this. So basically, to conclude, we can show that this method clearly improves the processing, the analysis and interpretation of key environmental parameters. So from classical graphs that are still useful, but not really quantifiable compared to now, where we display the environmental data in a more clear and easy to interpret way to identify the root cause analysis or the cause of mold growth. So the key environmental parameters, the impact of these are now precisely calculated through the knowledge of critical thresholds, and we can determine the cause, the probability, severity, and the moisture imbalance in a house, and then to direct to the most appropriate and effective rectification strategies in a building. So this is all for now, and now just to finish, just to show you where we are now. So we are in the proof of concept, testing, and future developments. From the results, we already knew this before, but we know that the lower the thermal envelope, the performance or the quality, and also insufficient ventilation, it has a higher likelihood of having mold growth. So from the results, we know that in most of the case studies that we researched, an inadequate ventilation was the main cause of mold growth. So, however, most solutions currently are based on adjusting temperature and humidity as a function of the heating system, or changing insulating materials to improve thermal efficacy of the envelope. So, however, there are other ways more cost-effective to reduce moisture, working with ventilation. But this requires more research and the link and assessment to different types of ventilation systems. So we are now, we want to demonstrate the potential of the diagnostic tool by testing moldy dwellings with needs of cost-effective solutions, like can be the city council properties or housing associations. So we want to perform some tests to look at the different ventilation systems and to find which is the most appropriate. And just to finish, we are now looking for commercial partners with software and hardware developers, manufacturers of environmental systems, in order to improve the functionality of the tool. So to having a more user-friendly tool, working with the data manipulation, the setup and the connection to heating and ventilation system to control this, and then to have a remediation and predictive tool that includes modeling and risk assessment. So we are considering different options for a final product. So if giving a service, like performing the monitoring and providing reports or mold-free certificates, or the idea of having a final tool, a kit tool with hardware, a software, and an APP, and so we are considering all this now. So that's all. So thank you for your attention.
Thank you, Paula, for a great